Here we are at lecture 4E, and this portion of the lecture is going to be dedicated to talking about our conjugate acids and bases and their role in equilibrium of acids and bases. So let's look at conjugates once again. Remember, so your conjugate acids and bases are those compounds that have the acid and base properties in the reverse reaction. So you have your acid and base, your Bronsted-Lowry acid and base in the forward reaction, and then your conjugate acid and base are the conjugates of those acids and bases, and they serve as the acids and bases for the reverse reaction. So we mentioned that the conjugate pair always differ by only a single H+, and so here we have our acetic acid. This was one of our first examples. So here it has an H, and here we see that the H and a plus is missing, so it's CH3CO2 minus. And here we have water and H3O plus, and so the H3O plus gained an H. We have two H's here, we have three H's here, and now we have this additional plus. So again, we just have to look for a single H plus difference between products and reactants in order to identify a conjugate pair. And those are the pairs that are in equilibrium with each other as H's move from one species to another. Now, in order to determine a conjugate's strength, remember we said that for strong acids and strong bases, their conjugate bases or acids are so weak that they are ineffective. So these two things usually go inversely proportional. So as the strength of an acid or a base goes up, the strength of its conjugate goes down. And so when you have strong acids and bases, the strength of their conjugates is so low that they're ineffective as acids and bases. But for those things that are weak acids and weak bases, they give conjugates that are weak bases and weak acids. So in order to determine their relative strengths, we can look at a table of Ka and Kb values. Now we know that from our Ka and Kb values that the K itself the values favor the reactants because our Ka or Kb values are so small. That means that reaction goes very little in the forward direction, and for the most part it goes fairly strongly in the reverse direction. So the larger the K, the stronger the acid or the base, and so that's why we can look at the K values to see which way things are going to be shifted relative to another acid. So if we compare the strengths of acids and their conjugate bases, the weaker the acid, the stronger the conjugate base. So remember, these things go like this, kind of inversely related. So the weaker the acid, the stronger the base, and the weaker the base, the stronger the conjugate acid. Okay, so just goes back and forth. So here's a table of different acids and their conjugate bases, and we can see how strength goes. So we see over here on the left we have acid strength going up, and on the right we have base strength going down. So if we look at something like HCl, we mentioned HCl is a strong acid. Its conjugate base is Cl minus, and we see that its base strength is lowest of all. All of these are right here. So HCl, H2SO4, HNO3. Notice that these are three of our strong acids right here, and their bases, their conjugate bases, are all determined to have neutral solutions because their strength is so weak. Water, or rather H3O plus, is just a water that's gathered a proton, and that's the strongest that these acids can actually be in water because of something called the leveling effect. You don't need to worry about that, but that's water's or hydronium's conjugate base there, H2O, and its acid is H3O plus. And then as we go down, we see the acids are getting weaker and weaker and weaker and weaker. Their conjugate bases are getting stronger and stronger and stronger as we go down. So here we have NH4 plus, a weak acid, and we have NH3, its weak conjugate base. And if we compared the K values, we would see that NH3 is a better base than NH4 is an acid. And then we finally start coming down here. We got things like water as a weak acid, and its conjugate weak base is OH minus. We have things like HS minus, no acid strength at all, but it does have a strong conjugate conjugate strong base, S2 minus the sulfide ion. So just kind of an interesting table. It just really indicates that that inverse relationship between the strength of an acid or base and its conjugate. Now, if we want to relate the Ka and Kb of a conjugate pair, those two things are related mathematically. We saw how the strengths of acids go back and forth there, and it turns out that if you take an acid's Ka, so an acid dissociation constant, and its conjugates Kb, and you multiply those two things together, so the Ka and the Kb of a conjugate pair will be equal to Kw for water. And so what that indicates is that an acid and its conjugate is affected by the value of the equilibrium for water. And so we have a nice little equation there. Ka times Kb is equal to Kw. Now, it is very important that this is obviously not any Ka and any Kb for any two substances. These must be the Ka and a Kb of a conjugate pair. If you take just any old Ka and any old Kb and multiply them together, we're just going to get some weird number that means absolutely nothing. So got to do the Ka and Kb of a conjugate pair. When you start looking at acid-base properties of salts, which I don't think that's something we're going to do in this course, it becomes very important what the Kb of a conjugate pair is. So here's just something to try here. We'll look at finding the Kb of the conjugate base of HClO. So HClO is hypochlorous acid. That's the acid that's present in bleach, or actually it's sodium hypochlorite. So to take the H off and put on a sodium ion there. So we've got HClO. When that H is removed, we've got a Ka of 3 times 10 to the minus 8. We've got its conjugate base, ClO minus, the hypochlorite ion. We want to know what is the Kb of that hypochlorite ion. So go ahead and try it on your own, and I will post a solution onto YouTube for that one. Now, we saw that when we were dealing with H plus ion concentrations or hydronium ion concentrations and hydroxide ion concentrations that were fairly small, we found an easy way to work with them using pH. Well, it turns out we can use that P calculation for Kas and Kbs to compare the acidity or basicity of different acids or bases, or even as you go more into organic chemistry and biochemistry, where you have really large molecules, you may want to compare the acidity of a hydrogen in different parts of a single molecule. And a lot of times they do that using these things called pKa's. And there you're actually looking at the negative log of the Ka of that particular hydrogen to come off in solution. So just like pH was negative log of hydronium concentration, pKa is negative log of the Ka, the acid dissociation constant. And pKb is negative log of the Kb, as you might imagine. So kind of like the way that pH works, the lower the pH is, the more acidic a solution is. Well, that means that the lower the pKa is, the stronger an acid is. Because remember, your Kas have those negative exponents generally for your weak acids. And so as you take the negative log, the smaller number in a negative exponent makes that number larger overall, and so as pKa goes down, that indicates a lower negative exponent in the Ka, and so the acid will actually be stronger. And the same goes for pKb. The lower the pKb, the stronger a base is. And again, very similar to how pH works. And if you have a conjugate pair, because your Ka times your Kb is equal to your Kw, which we have as 1 times 10 to the minus 14. So let's just go ahead and let's look and see how that works. So we know that for a conjugate pair, Ka times Kb is equal to 1 times 10 to the minus 14. That's the one there. There we go. If we take the negative log of both of those, we get pKa. And because we're taking the log of two things multiplied by each other, we can add their logarithmic terms, so pKb. And then if you take the negative log of 1 times 10 to the minus 14 for your kW, you get a value of 14. So for a conjugate pair, it's easy to work with the Kas and Kbs through the pKas and pKbs, because the pKa plus the pKb of a conjugate pair has to add up to 14. And again, that's assuming we're at 25 degrees Celsius. So one thing we don't do a whole lot with in this course, but you may see it in future chemistry courses if you continue to go on, is an idea of polyprotic dissociation. So all of the acids I've shown you up to now, we've just had a single H plus coming off in water. But there are some very common acids that can lose more than one H plus. Something as common as sulfuric acid, that I think is the most common chemical produced in the world. And then you have something like phosphoric acid, which is the acid you find in a cola drink, like Coca-Cola, Pepsi-Cola, generic cola. They all have phosphoric acid in it. You can actually see it on the list of ingredients. So again, phosphoric acid, it's actually something that's called triprotic because it has 3 acidic hydrogens, 3 hydrogens that can come off in solution. We can write the reaction a couple of different ways. We can write it this way, where we've got H3PO4 goes to 3H plus a phosphate ion. Now we have to be careful when we look at this reaction because it looks like we put phosphoric acid into solution and thoing, off come 3 hydrogen into the solution. And it doesn't quite work that way. What actually happens is that those hydrogen ions come off in a series of equilibria, and the equilibrium constant for each hydrogen coming off changes, and each hydrogen, it turns out, is harder to take off than the previous one. So let's look at the different equilibria that we have here. So here we have our first hydrogen coming off, and so we have H3PO4 plus H2O, and we're at equilibrium turning into H3O plus and H2PO4 minus. So it's got a pretty good sized equilibrium constant, 7.5 times 10 to the minus 3. As weak acids go, that's fairly substantial equilibrium constant. So it's a pretty good weak acid. Now we've got this species right here, this H2PO4 minus. Okay, once that species is formed, it's got 2 choices of where to go. It can re-react with the H3O plus and reform H3PO4, or it can react with another water molecule and lose another H plus. And so we've got H2PO4 minus plus water going to another H3O plus HPO4 2 minus. So now we've lost another hydrogen off the parent molecule, and notice that equilibrium constant now, 6.2 times 10 to the minus 8. That is fairly small. That is about 100,000 times smaller than the previous equilibrium constant. So it is much harder to take that second hydrogen off for a variety of reasons. I always like to think about it because you're trying to pull something positive now away from something that is negatively charged. Our H2PO4 is negatively charged, and we're trying to pull a positive charge away from that. And so I think there's a little bit of grab there. I'm sure there's lots of different reasons that get into more detail than we want to, but I like to think of it that way. It's an easy way to think about it. Now, what about our third hydrogen? Well, we've got our HPO4 2 minus here. It's still got a hydrogen that can come off. So it can either regain an H plus from H3O plus and go back here to reactants, or if it runs into a water molecule, it can become another H3O plus and PO4 3 minus. And we see that the equilibrium constant has become extremely tiny, 4.2 times 10 to the minus 3, another factor of 10 to the 5, so about another 100,000 times harder to pull off that third hydrogen. As it turns out, that third hydrogen is actually fairly difficult to pull off even with a strong base. You got to have a pretty high concentration of base to get that third hydrogen off when you're in solution. So a lot of times what happens with this is when we're doing math on like what would be the acidity of this, and you could drive yourself crazy by going, oh my god, I got 3 hydroniums I have to factor into account of all these different equilibria. Really, this is the only one that's going to matter because it's so much stronger than the other two. It's going to be the one that has the greatest effect, and it's probably the only one that you'd be able to measure against the other two. So a lot of this is what I just said. So with our polyprotic acids, they do give us a challenge because they're capable of donating more than 1 H+. Each of those hydrogen ions coming off has its own Ka value. However, a lot of times the ionization constant for the second and even the third H+ is so much weaker than the first one that only the first ionization needs to be considered. There's some calculations you can do where you calculate the pH after the first ionization, and then if you then take into account the second ionization, you'd find that your pH to where you can measure it is still exactly the same. It is different a little farther out in the decimals, but the problem is that your devices can't measure out that far. So a lot of times we will only do that first ionization, use that first Ka, that first hydrogen coming off to determine what a pH might be for a polyprotic acid. Now there's also things called polybasic bases, which means that those are bases that can accept more than 1 H+. And a lot of times you find the same kind of deal where accepting that first H+ is the only one that matters. It's much more difficult to put that second hydrogen on or even a third one. And here's just a brief table of some different Ka values for some polyprotic acids. So something like sulfuric acid is a polyprotic acid. The first H+ is strong, in other words, it comes off very readily. The second one is technically weak. It's one of the strongest weak ones we have. And if any acid is present at all in that solution, this hydrogen comes off, or I'm sorry, any base present at all, this H+ comes off very easily. For something like oxalic acid, this is a compound that people use to clean the inside of radiators in their cars, or they can clean humidifiers or air conditioners with it. You see they have a difference of 10 to the minus 3 between those. Sulfurous acid 10 to the minus 6th. We saw the phosphoric acid. Now citric acid has an interesting situation where you've got 10 to the minus 4, 10 to the minus 5, 10 to the minus 7. There's a good chance that 10 to the minus 4 and 10 to the minus 5 values would both have to be taken into account when calculating a pH, simply because those Ka1 and Ka2 values are so close together. There's not much separating them, and so this Ka2 probably does contribute a measurable amount of H+. So that would be a more complex problem. But then we get back down here to ascorbic acid, which is vitamin C, 10 to the 7th difference between the two constants, and carbonic acid, which is what you get when carbon dioxide dissolves into water, and so they have a 10 to the minus 4 difference, or 10 to the 4th. So usually they're quite a bit different, and a lot of times we only have to worry about calculating or using the first Ka to calculate a pH rather than successive H's that come off there. Again, we're not going to do a whole lot with that, but I thought it should be something that you see. All right, so that finishes up our idea of conjugates and how all of this works. If you have any questions on any of the content on this one, please let me know.